Hey everyone, I'm Yu Chen and this is Yu. We are the Triple Z team because three of our team members share the same last name. Okay. And our project is predicting the click-through rate of the sponsor search. So first of all, let me have a quick review of the background and motivation of this problem. Suppose that a user submits a query to the search engine, and in this case it is insurance, and the search engine will return the user a search result page. At the top of this search results page, there will be at most 3 advertisements shown to the user, and the user will choose to click or not click some of them. So our task is to predict the probability of each of these advertisements being clicked by the user. So our available information for the prediction is including the search query submitted to the search engine, the user's profile that is acquired from the user's login account, including an account ID and some demographic information about the user, that is the sex and gender and the age of the user. We also have a series of features that describe the characteristics of the ads, including the advertiser's identity, the position, the presenting order of the ads, the title, the URL, and the description of the ad. And for experiment, we have used the KDD Cup 2012 dataset that is collected from Soso.com, the third largest Chinese search engine in the Chinese market. And it contains 641,000 distinct advertisements that have been shown to the user for 235 million times. So this is the largest data set of this kind that have ever been released to the public. So in the last time, in the midterm presentation, I have reviewed some of the existing state-of-the-art methods for this problem. So let me have a quick recap of them. The empirical counting method is just predicting the future CTR by the ratio of the number of clicks and the number of impressions in the past. And we also use the smoothing factor beta to deal with the extremely low frequency advertisements. The position model further incorporates the position bias into the prediction to further improve its accuracy. And it is based on the observation that the user will tend to click more on the higher ranked advertisements, even if these advertisements are not that relevant to the user's information need. And the logistic regression model is a classical approach just to incorporate all the information we have as features into prediction. So we use the linear combination of features to form a score Z and use the logilink function to map this real value score to the 0 to 1 probability range. So all of these three methods are simple and they can be scalable to large scale data set, but they all have limitations. So as I've mentioned in the previous presentation, the first two methods, the empirical counting and the position click model uses only a limited set of features. And the logistic regression model can only generate the linear separator of the feature space. So our experiment has also shown that none of these models can perform the best in our specific problem. So we have proposed a novel method for this problem, which is called personalized collaborative filtering, or PCR for shorthand. And actually, this model performs very well in practice. And so this is the KDD Cup 2012 leaderboard. It's the latest version of today. And our result has ranked at the top position among the 200 players and nearly 2,000 different submission entries. So how do we achieve this remarkable result? Let me invite Ning to describe our model and the inference algorithm in more details.
Thanks, Yuchen. So this is our approach, and as Yuchen mentioned before, all those data log methods have some limitation. Either they haven't made full use of the feature that we could have, or they don't model the relationship between the user search intent and the advertisement content. And here we use three features, which is the X is the advertisement content. It includes the advertisement title, keywords, the advertiser ID, and so on. And Y is the user's profile feature. It includes the keyword tokens, the user gender, age, and the user search frequency. And the B here is other features, other context features. It includes the precision, the ad, the session depth, the advertisement ID, the frequency, and so on. And what we want to do here is to model the relationship between the user's profile feature and the advertisement content feature. We do that by introduce two matrices here called U and V to map the feature vector X and Y to a lower k-dimensional feature vector. And we use the inner product to model the similarity between them. Also, we introduce prediction bias here, W transport B, and we use appropriate function to map the real value to the CDR rate lie between the 0 and 1. And all the parameters have the Gaussian phi here. So the goal of this model is to infer the parameters UV matrix and the W vector. And it's not easy to do that because first of all, the log likelihood is not concave, so we don't have a global optimal. And also, since we have millions of users and millions of records of queries, it's hard to fit all the data into memory. So we need to have an online format of the learning and inference. And also the data is not evenly distributed, which means some of the ads are very frequent, while some of them are not very frequent. So we need to maximize the posterior instead of maximize the likelihood to avoid the overfitting. For inference, we use the variational Bayes inference, and the basic idea is to approximate the joint posterior distribution P, U, V, W given data implied by the independent Gaussian distribution. All of these three terms are the independent Gaussian on the element U and on the element of the matrix U, V, and W. And we infer and we learn the approximate Q by minimizing the KL divergence between Q and the original posterior. So it's the normal pipeline to do the variational Bayes inference. And here is the vector graph model that we have. And we, as we can see here, we assume these three parameters are independent independent, and we use the message parsing to do the inference. And first we compute the message 1 here. It is just a linear combination of the Gaussian, and then we pass down the message to 2 and compute the message 2, 3, and 4 until we observe the true data, that is whether the user clicked the ad or not. And then we update the posterior distribution of this R, and then pass the message up and compute the message 5, 6, 7, and 8. And then the final step is to update the posterior of the UVW. And to make it more scalable, we implement in a multi-code parallelization scheme. And suppose that we can divide the data into n parts, B1 to Bm, and we can get the approximate posterior for those n parts, and we use this Bayes formula to get the approximate posterior for the whole data set. Now let's ask Yuchen to introduce more details in the experiment.
So thanks, Zhongying. Let's return to the practical implementation of the algorithm. So achieve the good performance, the selection of features is almost as important as the selection of the model. So I'm going to report briefly the table of features we used for our model. So for the features of the advertisement content, we use the keyword, the advertisement title, and the advertiser's identity. For the features of the search intent, we use the query tokens, the user frequency, which is the number of appearance of the same user in the data set, and the demographic of the user, including the gender and age. So for the purpose of the best performance, we have discretized all the features into integer values. It means that for every feature of n possible integer values, we have generated a binary feature vector associated with this feature with all coordinates equal to 0 except for the one coordinate associated corresponding to the feature value of the specific instance. So this binary feature vector is used as a part of X or Y and in the training process. And in order to control the dimensionality, we have to do some hashing strategy. So for example, for the word tokens in the keyword query and the title features, we have hashed all the word tokens into 20,000 different hashing bins, so that the dimensionality of these features is no more than 20,000. The features of the prediction bias is very similar in the form of the previous two, in which we do the discretization and then produce the corresponding binary vector and use it as a part of B. So besides the directly available information in the source field, which is the advertisement ID, the position and depth, we have also generated some generalizable characteristics of the data set that could be very helpful in the process of prediction. So these characteristics includes the frequency of the query, the frequency of the advertisements, the length of some sentences like query sentence, the title, the description, and we also computed some average CTRs as sub-models with respect to a various of indicators like the query, the user, the advertiser's identity, and the word tokens. So the experiment has shows that this characteristics has a huge boost to the overall performance of the accuracy. So we evaluate the performance of the models in the online evaluating system of the KDD-CAP, and it is based on about 20 million testing instances that we cannot access their click labelings directly, but we can only submit the predictions of ours and see the report of AUC, which is the area and the curve, the standard metrics for evaluating such problems. So the experimental result is as expected. The click model is slightly better than the empirical counting because we have incorporated the position bias. And the logistic regression model is better than the click model because it has used the generalizable characteristics we have developed. So finally, the PCF model, the personal collaborative filtering, is the best over all models. And because it has the ability to measure the similarity between the user's intent, the personal intent, and the advertisement's content. So in addition, we have also found out as the dimensionality of the projection increases, the performance of accuracy also increases. So the best performed model is the PCF with k equals 30. We also did the experiment locally with the log likelihood matrix to evaluate. So in local experiment, we have divided the original data set into two pieces with the training and testing pieces. And the amount of data among the two pieces of data set is 4:1. And we use the log likelihood, negative log likelihood metric with respect to different presenting positions. And the experimental result is kind of consistent with the previous experiment, with the PCF with the largest dimension of projection lead has the best performance, and followed by the PCF with the lower dimension of projection, and then further followed by the logistic regression and position model and empirical counting. So here the baseline is another very trivial method. It's just to predict every CTR in the testing set by the average CTR of the training set. And so it is, you can see that it is much worse than other methods we have mentioned about. So both of these experiments has shown that our method is, our approach as proposed is effective and their result are consistent. So that's all. Thanks for listening, and any questions?